We'll also be taking upon the topic of control strategies and what are the different control mechanisms present and how are they being implemented and what are the different control strategies implemented to control the output power. All those things we'll be seeing in this chapter. And again, not only the characteristics of the turbine play an important role, but also the characteristics of wind in a particular area where the turbine is being established also plays an important role. So that also we are going to study. How are we actually, in order to choose a particular area, let us say if you are choosing a particular area to establish a wind turbine or a wind generating system, then how are we choosing that? There should be some rules, right? There should be some way in which we are taking this particular area into consideration, right? We have to know some certain things about that area. We have to analyze certain things about that area in order to make sure that we have taken a right choice, right? So what are those parameters that are playing an important role in understanding an area and select whether and knowing whether it is suitable for the establishment of the wind generating station or not? These are the points which we are going to see in this chapter. Okay, so first thing is we are going to see about the characteristics of the turbine itself. First of all, how does it operate under different conditions and what are the optimal conditions and how is it operating under optimal conditions? All those things we will be seeing. That is the first part. The second part is with the control strategies. What are the different control strategies present and how are they being implemented? All those things we will be seeing in the second part. Then, and the third part is to understand the area. If you are taking a certain area and trying to establish a wind generating power station, what are the parameters which we need to take into consideration and how are we analyzing that particular area in order to make sure that we are taking a right choice? Okay, how are we establishing whether that area is suitable for wind power generation or not? Those are the points, those are the topics. That is, we are dividing this total chapter into three parts. First part is characteristics of the wind turbine itself. The second part is the control strategies, and the third part is the wind characteristics in a particular area. That is the total outlay of the what do you say, this chapter, second chapter. Now let's start the class. So uh, So first thing which we are going to see is the power speed characteristics. What is this power speed characteristics means? This is nothing but the characteristics between the mechanical power extracted from the wind, mechanical power extracted from the wind and rotor speed. The characteristics drawn between the mechanical power extracted by the wind from the wind and rotor speed. If you just look at this is the typical power speed characteristics which we are going to analyze and how what are the different parameters on based on which we are drawing these parameters, sorry, we are drawing these graphs. We'll see. Okay, the first thing is for each wind speed there is an optimal turbine speed at which the wind power extracted is maximum. The first thing is we have two types of speeds. First speed is the wind speed, the second speed is the rotor speed. So in order to make sure that we are extracting the maximum power from the wind at a particular speed, we need to make sure that there is an optimal turbine speed at which the power extracted will be maximum. How are we establishing that there will be an optimal turbine speed? Means we have seen in the last chapter. In the last chapter, we have discussed various powers and how those equations are there and what are the parameters that are being affected in order to get the maximum power and all those things. There we have established that there is an optimal speed at which the turbine should be rotated in order to get the maximum power, right? That we have actually done, that extract that derivation we have done, if you people remember. So We know that there is an for each wind speed there is an optimal turbine speed at which the wind power extracted will be maximum. So this we know, we have established this. Okay. Okay, such family of curves can be represented by a single dimensionless characteristic curve named cp dash uh, tsr, right, delta, sorry, not delta, lambda, CP lambda curve, where power coefficient is plotted against TSR. This is also the plot which we have seen starting itself. In the starting itself, we have seen this plot, right? The curve of power coefficient versus tip speed ratio. This thing we have seen. We have seen for it the different types of windmills, and we have also established that Darius rotor and high speed propeller type rotors are what do you say, ideal for the power generation, and because of the less TSR and less power coefficient, these Savinus rotor, Dutch type windmills, and again multi-blade water pumping windmills are not suitable for the power extraction. This we have already established. The same thing he is saying, instead of writing a family of curves like this, that means at each wind speed we are writing a curve and establishing the what is the maximum rotor power and rotor speed, and all those things. Instead of taking all these curves, these can be represented using this single curve which is power coefficient versus tip speed ratio. That is what he's saying. Okay. Now for a given turbine power coefficient not sorry for a given turbine power coefficient not only depends upon TSR but also blade pitch angle. TSR is the tip speed ratio. It depends on the tip speed ratio. We have established that, we know that, we are done with that. But we need to understand that the power coefficient not only depends upon the TSR but also it depends upon the pitch angle, blade pitch angle, the angle at which the blade is being rotated. That is the pitch angle. Now, next, figure 1.18 shows typical variation of power coefficient with a TSR with the blade pitch angle. This is showing us both with pitch angle as well as the tip speed ratio. Here he is showing us what do you say, power coefficient versus tip speed ratio at a different pitch angles. You can see that the pitch angles have been shown here. Alpha is equals to 0, alpha is equals to 2, alpha is equals to 4, and alpha is equals to 6. They have drawn 4 curves depending upon the pitch angle. How are we establishing, again, how are we establishing this power coefficient versus tip speed ratio? Means this curve, we are just consolidating these total curves into one curve. We are consolidating the family of curves where the power and the rotor speed are being plotted into one curve. That curve is nothing but the power coefficient versus tip speed ratio. This curve, again, what we are doing is, this curve only establishes the relationship between power coefficient and TSR, but the power coefficient also depends upon the pitch angle. So in order to establish the relation between pitch angle, power coefficient as well as tip speed ratio, we are drawing another set of curves where here we are seeing power coefficient versus tip speed ratio at a various pitch angle values. Okay. Next, the mechanical power transferred to the shaft is given by this equation we have already seen. This similar equation we have already seen. Now, if the turbine is having a radius r, if the wind turbine is having a radius r, then we can just we can just replace area, that is we have here A is the area, right, area of cross section, right. That area of cross section can be represented by, if the radius is r, then pi r square. We can replace A by pi r square. That is what we are doing here. That is what we are doing here. Okay. Next, for a given wind speed, power extracted can be maximized if Cp is maximized. So just by looking at this equation, we can say that for a given wind speed, power extracted can be maximized if Cp is maximized. At an optimum value of Cp, say Cp opt, occurs a occurs at an optimal value of lambda, say lambda optimal. He is taking an optimal value of power coefficients and an optimal value of tip speed ratio. This means that for varying wind speeds, the rotor should be adjusted properly to adhere always to this value of lambda for maximum mechanical power output from the turbine. So we are saying there is an optimal value of tip speed ratio. So we need to make sure that whenever there is a varying wind speed, the rotor should be adjusted proportionally to obtain this tip speed ratio, to obtain this optimal tip speed ratio for getting the maximum power output, for getting the maximum power output. Okay. Now, using the relation lambda is equals to omega r by V infinity, we are establishing this relation. This relation we have already established in this one, right? We have already established when we studied the tip speed ratio. This relation, the same relation he's taking, and he's just modifying the equation 1.14. He's just modifying the equation 1.14. Okay. Now, Pmax is equals to just using the optimal values of Cp and optimal values of tip speed ratio. He is just modifying the equation accordingly. Now, thus the maximum mechanical power output can be extracted from maximum power output that can be extracted from wind is proportional to the cube of its rotor speed. Just by looking at this, Pmax is nothing, is proportional to omega cube. Pmax is proportional to omega cube. This is shown in the figure 1.17. This is shown in the figure 1.17. What is figure 1.17 means? This is the figure 1.17. That means we are plotting power and rotor speed. Power and rotor speed. Here, if you just look at this diagram, we can say that there is an optimal rotor speed for a wind speed. For every wind speed, we have an optimal rotor speed, and at which the power will be maximum. So this is the power speed characteristics. Next topic is the torque speed characteristics. Here, what we are going to do is, why are we studying this torque speed characteristics of a prime mover? Means it is useful to establish, it is useful to properly match the load and ensure stable operation of the electrical generator. We know that the load, whenever there is a source and a load, we need to make sure that the source and load are matched properly in order to get the maximum power output, right? So that is what is we are going to do in torque speed characteristics. By studying torque speed characteristics, we can make sure that our load is being matched to the source and ensure the stable operation of the electrical generator. Okay, the typical torque speed characteristics of a two-blade propeller type wind turbine, the Darius rotor and the Savonius rotor are shown in figure 1.19. Okay, so here we are seeing, here he is giving us a graph of different types of torque speed characteristics of different types of rotors. Here we can see the first graph which we are seeing, that is A is the Savonius rotor. So you can see how the Savonius rotor is having. So we can just look at if we just look at this particular graph, we can say that the torque at the starting is maximum and it is getting reduced as the speed is increasing. Okay, torque is maximum at the starting and then it is getting reduced, just it is declining, that we can establish. Now look at the Darius rotor torque speed characteristics. Here you can see that the torque is 0 at the starting and it is getting increased to a certain value and then getting decreased again. It is getting increased to a certain value and then getting decreased. So it has a maximum point when you are looking at this particular when you are looking at this particular diagram, sorry, figure, you can say that there is a maximum point at which the torque and rotor torque speed characteristics has a maximum point in case of a Darius rotor. Now, next is the high speed propeller type rotor. Here we are taking second, what do you say, two blade uh, high speed propeller type rotor. Now look at the difference between Darius rotor and the high speed propeller type rotor. We know that the Darius rotor cannot start by itself, right? It cannot start by itself. So the starting torque is always zero. We know this, right? We have said that when we studied about the Darius rotor, we have said that there should be some other means, external means to start the Darius rotor. The starting torque should be provided to the Darius rotor. So that's why we have the torque at the starting as zero. Whereas we come to the when we come to the high speed propeller type rotor, this has a starting torque. It doesn't need any external, what do you say, push or external uh, energy to start, right? It can start by itself. So there is a starting torque, and then it is getting it after, as we are what do you say, as we are increasing the speed of the machine, we are seeing that the torque is getting to a maximum point and then getting reduced. The torque is getting to reaching a maximum point and then getting reduced. Because of this nature of the torque getting increased to a particular maximum point and getting reduced, the high speed propeller type rotor as well as the Darius rotor are used for the electrical power generation. Because of this nature, these two are used for the electrical power generation. And as we have seen in case of the as we have seen in case of the Savonius rotor, there is a starting torque, but it is getting reduced as the speed of the turbine goes on increasing. So this cannot be used for the electrical power generation. Now, the profiles shown in the power curves as power and torque are related. Okay, here what he is going to establish is, here whatever you are seeing, the profiles you are seeing, these can be modified as power curves also. These can be modified as power curves also. How are we modifying this as power curves? Means we have the relation torque is equals to power by rotational speed. Torque is equals to power by rotational speed. By just modifying this, by using this relationship, we can establish that the power curves of the are also power curves can also be in the same way as the torque curves. Okay, the power curves can also be redrawn using the torque curves. Okay, from this just this okay. Now, from equation 1.42, that is from the starting in the, sorry, I'll show you 1.42. This is the equation 1.42, that is P max, mechanical power output, right? Next, by using that equation, what is trying to tell is, when these are operated at the optimal operating point, the relationship between the aerodynamic torque and the rotational speed is, by he is using that particular equation and he is establishing the torque. Now we know that the torque is nothing but power by omega, right? Power we have found out there. By using the power itself, what he is doing is divided by omega. We are just dividing it by omega and writing the torque equation. For high-speed propeller type rotor and Darius rotor, we can see that the torque reaches a maximum at a specified rotor speed, and this maximum shaft torque varies approximately as the square of the rotational speed. Okay, is it true? Let us see. Okay, he's just saying that this maximum torque varies, maximum shaft torque varies approximately as the square of the rotational speed. Is it's just saying that, okay. Even if you look at this diagram, you can say that, right? Where if you draw a straight line by just looking at the straight line and maximum power, you can say that this has that shape of square shape, right? I mean, not square shape. When we plot the diagram, when we plot the graph x is equals to y square, you will get a curve, right? The same curve is being replicated here. Okay, Approximately, not exactly, of course, but approximately we can say that. Now, in case of the electrical production, the load torque depends on the electrical loading, and by properly choosing the load, the torque can be made to vary as a square of rotational speed. So we whatever whenever we are going for a electricity production, the main aspect here is in order to sorry okay, we know that there is a law called as the maximum power transfer theorem, right? In that maximum power transfer theorem, we know that whenever there is a matching between the source resistance as well as the load resistance, only then you will find the maximum power transfer between the source and load. We know this already. This is an established law. In the same manner, in order to maximize the power generation, what he's saying is the load torque depends upon the electrical loading, and by properly choosing the load, the torque can be made to vary as the square of the rotational speed. So we need to choose the load properly in order to make the torque vary as the square of the rotational speed. The choice of the proportionality constant of the load is very important. Here, whenever we are talking about this one, power to be square of the rotational speed, we are just saying those are proportional, right? Those are not exactly equal to the squares. So, to make sure that we are having a nice propose we are having a load which is very very good for our maximum torque production. Now there is these are proportional, right? So we'll establish a relationship between these two using a proportionality constant. So the value of this proportionality constant also plays an important role. At the optimal value of the load curve, the optimal value of the load curve follows the maximum shaft power. Follows the maximum shaft power. At the optimal value, the load curve follows the maximum shaft power. So, okay, but at higher value, the load torque may exceed the turbine torque for most speeds. Okay, consequently, the machine would fail to speed up above a very low value. So, we need to make sure that the constant is lower than the optimal value, lower than the optimal value, but also to make sure that it is not a higher value. Okay, it should be in a if the constant is lower than the optimal value, the machine may overspeed at the rated wind speed, activating the speed limiting mechanism. We know that we have a mechanism at which will stall the wind turbine if there are high speeds, right? If there are high and dangerous speeds, we are having a mechanism which is called as a stall control. We'll see how that works and everything. Which is called as a stall control, which will stop the turbine at higher speeds in order to protect the turbine from higher wind speeds. Okay, if the constant k is lower than the optimal value, if we are having a constant k which is lower than the optimal value, the machine may overspeed at the rated wind speed. Okay, activating the speed limiting mechanism. So we need to make sure that the proportionality constant of the load needs to be selected in such a way that it should not overspeed the machine. It should not overspeed the machine, as well as it should not fail the machine. As well as it should not fail the machine. So it should not be a very low value and it should not be a very high value. First thing. The second thing is it should be lower than if it should be like in between a very small narrow range is there in which we can select this what do you say, k value. Okay, what is this range means? About 10 to 20% of the optimal power curve. We have to make sure that whatever the range or whatever the low constant value k value is there, that should be only about 10 to 20% of the optimal power curve. Note that at the point of maximum torque is not equal to the point of the maximum power. We need to understand that the maximum torque doesn't mean maximum power. Maximum torque doesn't mean maximum power. At the power output, as the power output is the product of the torque and speed, it also has maxima that vary as the cube of the rotational speed. Okay, as the torque, as the power is the output of torque and speed. We know that the torque varies as the square of the rotational speed. So, and the power is nothing but the torque into speed. So, we know that there is a maxima of the power that varies as the cube of the rotational speed. Just multiplying it, right? We have seen this. P max is proportional to omega cube. In the last discussion, that is for the power speed characteristics, we have seen that the P max is proportional to omega cube. That is what he is establishing. Now, the matching characteristics of the load can make the load curve pass through the maximum power points at all wind speeds. So we need to make sure that the load characteristics are in such a way that it that the load curve passes through the maximum power points at all wind speeds. Okay, and let's see here. If you just look at this diagram, we know that the torque is this is nothing but the torque speed characteristics, right? We know that the torque is proportional to the square of the speed. All these things we know. Now, if the value of k, if the value of k is less than the optimal value, let us say the k value is less than the optimal value, that is k1, in this case k1. Now if you just look at this diagram, if you just look at this graph here, k1 n square, when you draw the graph of the k1 n square, that k1 n square is not establishing the maximum power points. It is not passing through the maximum power points. It is making the it. If you just look at this diagram, you can say that the power output will be zero at certain points, right? In the same manner, if k is greater than k2, sorry, if the k is greater than the optimal value, that is k2 here in this case. Now if you look at this diagram, here also you can say that there is no optimal power, right? The power output which we are going to get is not the optimal power output. So we need to make sure that the k value is in such a way that the load curve passes through all the maximum power outputs, maximum torque points. That is how they have to establish the k value. If you just look at this diagram, you can see that k n square is the load curve, desired load curve, in order to make sure that our power output is maximum. Okay, for the generators that feed power to the grid, the torque speed characteristics are tuned using the power electronic controls. What we are going to do is there are different types of controls. We'll see what are the different types of controls. In that types of controls, we have power electronic controls. Using these power electronic controls, we are going to tune the torque speed characteristics in such a way that we'll get the maximum power, all we'll get the maximum power always. Okay, in terms of the power coefficient, the aerodynamic torque becomes, he is just establishing the aerodynamic torque here. Instead of using cp by lambda, he is just using ct and calling it as the torque coefficient. Okay, this is the second topic, my torque speed characteristics. So we can see that we need to understand the torque speed characteristics so that we get the maximum power output from the turbine. So we need to make sure that our proportionality constant is in such a way that the load curve always passes through the all the maximum torque points in order to establish that we get the maximum power outputs. So these are the two characteristics which we need to understand. The first one is called the power speed characteristics. The second one is called the torque speed characteristics. Next topic is wind turbine control systems. Wind turbines require certain control systems, that we know, right? It needs to have some control mechanisms in order to make sure that it works properly. So what are those control systems? We are going to see now. Horizontal axis wind turbines have to be oriented to face the wind. In high winds, it is desirable to reduce the drive train loads and protect the generator and the power electronic equipment from overloading by limiting the turbine power to a rated value up to the furling speed. Okay, before even understanding what is furling speed and all those things, the horizontal axis turbines should always be oriented to face the wind. It should be always opposite to the wind. We have to make sure that the orientation is always opposite to the wind. But in case of the high wind speeds, when there are high wind speeds, we need to make sure that our generator, drives, and the power electronic equipment are not overloaded. So what we are going to do is we are going to limit the turbine power to a rated value up to the furling speed. That is, furling speed is nothing but the wind speed at which the turbine generator will shut off and stop generating power. Okay, that is the maximum speed at which the machine can operate without damaging itself. Okay, so if it is beyond the furling speed, then the machine will get damaged. If that is like a threshold, okay, threshold value. If that threshold value is attained, the generator will stop, the turbine generator will stop, and the electricity will not be produced. So we should make sure this, that the limiting power should be there. There should be a limiting power up to the furling speed. When the machine will shut off, at that time we'll have this at that point we should have a limiting turbine power. That means we need to make sure what is the turbine power at that furling speed. We need to calculate what is the turbine power at the furling speed and make that as the rated value. Make that as the rated value. At gust speeds means, gust means sudden increase of speeds of wind for a very short time. Okay, only for a short time. The generator should be stalled. What happens is, at the gust speeds the generator will be stopped. Okay, it will be stopped. Again after the gust will be, after the short increase of speeds will be gone, then the turbine will be restarted. Then the turbine will be restarted again. So we have two types of what do you say, speeds. Mean the first one is the furling speed, the second one is the gust speed. Furling speed means the the turbine generator will shut off and stop generating. The turbine generator will shut off and stop generating. Okay, gust speed is just sudden increase of speeds for a short time. Just sudden increase of speeds for a short time. At low and moderate speeds, the aim should be capture power as efficiently as possible. Our main aim should be to capture power as efficiently as possible at moderate and lower wind speeds. Next, rated wind speed. Rated wind speed is the minimum wind speed at which the power turbine produces its designated power output. Rated designated power output, that is nothing but the rated power output. Generally, this rated wind speed will be around 9 to 16 meters per second. Okay, now just look at this number, that is 9 to 16 meters per second. That will be your rated wind speed. That will be your wind speed at which the generator will start producing electricity. Now, when we have discussed about the what do you say, control equipment and all those equipment in the last class, that is in the last topic of the last chapter, we have said that there is a gearbox, right? Why do we need this gearbox? Means, look at the speed of the rated wind speed. Look at the rated wind speed. It's just 9 to 16 meters per second, but our generator rotates at 1500, right? Minimum 1500 rpm. So in order to bridge this gap of 9 to 16 meters to 1500 rpm, what we are going to do is we are going to put a gearbox there. Okay, now the choice of the rated wind speed depends upon the wind speed characteristics of the area. That is our next topic, that is wind speed characteristics. How these wind speed characteristics are there, and what is the optimal value of wind speed at that particular area. That is what we are going to understand. And based upon this value, we are going to establish what a rated wind speed turbines have to be used in that particular area. Okay, next, the generator rating is chosen so as to utilize the mechanical output of the turbine at the rated wind speed. So first thing we are establishing the rated wind speed using the wind speed characteristics of the area. So we are going to analyze the wind speed characteristics of the area and then establish the rated wind speed, that is the wind speed at which the generator will be operating. And then after establishing the rated wind speed, we are going to choose the generator rating such that it can utilize the maximum power output, sorry, maximum mechanical power output at the rated wind speed. So first thing is understanding the wind speed characteristics of the area, then rated wind speeds, and then generator rating. Okay. Next, but there are different types of controls needed. So what are different types of controls we have is, the first one is called as the pitch angle control, the second one is called as the stall control, the third one is the power electronic control, and fourth one is yaw control. We'll see each one of this in detail. So first one is the pitch angle control. Okay, what does this pitch angle control do? That is what we are going to see. Changes the pitch angle of the blade according to the variations, sorry, according to the, sorry, sorry, according to the variations in the wind speed. Okay, so it changes the pitch angle of the blade according to the variations of the wind speed. So it will be monitoring the wind speed continuously and then changing the pitch angle of the blade accordingly. High efficiency can be achieved by continuously aligning the blades in the direction of the relative wind. When we need to get higher efficiency, when we are aiming for higher efficiencies, what is the main concern which we need to make sure is the blades are always in the direction of the relative wind. That we need to make sure. Now, pitch angle control, when a pitch angle control mission is there, as the wind speed exceeds its rated speed, the blades are gradually rotated about the longitudinal axis and out of the wind direction to increase the pitch angle. This reduces the aerodynamic efficiency of the rotor and decreases the power output. So what we are going to do is, when the wind speeds exceed the rated wind speed, this pitch angle control, what it does is, it gradually rotates the blades along the longitudinal axis. And by just look, okay, we know that the pitch angle is nothing but the angle at which the blade is being put together, right? So now you're, if you are just moving this to like this along the longitudinal axis than the horizontal axis, we know that the pitch angle is nothing but the angle by horizontal axis. If this is not being done, if it is moving in the longitudinal axis, what we are doing is, we are taking the blades out of the wind direction. We are taking the blades out of the wind direction, out of the wind direction, and making sorry, and increasing the pitch angle out of the wind direction to increase the pitch angle. This reduces the aerodynamic efficiency of the rotor and decreases the rotor output. So why are we decreasing the rotor output here? Means, in order to make sure that our machine do not get overloaded. Okay. When the wind speed exceeds the safe limit of the system, the pitch angle is changed so sorry is changed that the output power reduces to zero and the machine shifts to stall. Stall means stop. Okay. Wind speed when the wind speed exceeds the safe limit of the system, that is nothing but the furling speed. If the wind speed is limiting the speed is more than the furling speed, the pitch angle is changed so that the output power will be zero. We are going to make the pitch angle such that the output power is zero and the machine is stopped. After the gust passes, the pitch angle is reset and the turbine is restarted. So if that is the wind speeds exceed the safe limit, in that case, if it is more than the furling speed, then we are going to stop the machine. If it is just a gust speed, that is just it is and temporary increase in the speed, then what we are going to do is, after that temporary increase in the speed is done, then we are going to reset the pitch angle and restart the turbine. Okay, we are going to reset the pitch angle and restart the turbine. Now, at normal wind speeds, the blade pitch angle should ideally settle to a value at which the power output is equal to the rated output. If there are no abnormal conditions, if the conditions are normal, how much should be the blade pitch angle means the blade pitch angle should be such that the power output is equal to the rated power output. Okay, the power output should be equal to the rated power output. Now, this is the feedback loop for the pitch angle control. Just look at this diagram. Here we have a gearbox, a generator, a pitch actuator, pitch controller, and we have a summation point at which we are going to take P command and P measure. Command in the sense here P command is nothing but the reference pitch angle. P measured is the measured pitch angle. Okay. Now, the input of the power angle controller is an error signal arising from the difference between electrical power output and the reference power. That is what we are saying. Power measured, we are going to take the difference between the power required and the power measured, and this will be your error signal which will be continuously fed to pitch controller. Now, the pitch controller operates the blade actuator. Pitch controller operates the blade actuator which in turn controls the pitch angle. That is, here the pitch controller gives it to the pitch actuator. Here blade actuator or the pitch actuator are the same. What we are going to do is we are going to change the blade angles, that is the pitch angles, based upon the pitch controller values. Now, during operation below the rated speed, the control system endeavors the pitch the blade angle that maximizes the rotor efficiency. If there is if the operation is below the rated speed, if you are not even getting the rated speed, we make sure that the blade angle maximizes the rotor efficiency. The efficiency is getting maximized. We make sure that the efficiency which we are getting is maximized. The generator must be able to absorb the mechanical power and deliver to the load. So we need to make sure that the generator, whatever we are establishing, should take the mechanical power and deliver it to the load. Hence, so if you are just operating, if you are just if the operation is below the rated speed, we are making sure that the rotor efficiency is maximum. If the rotor efficiency is maximum and we are monitoring it continuously, then the mechanical power which we are going to get will also be varying continuously. So we need to make sure whatever the mechanical power variations are there, those are being absorbed by the generator and those are being delivered to the load. Okay, so the the generator output power needs to be adjusted simultaneously. So whenever there is a change in the pitch angle, there is a change in the mechanical power output and there is a change in the generated power output. So all these things should be adjusted simultaneously. All these things should be adjusted simultaneously. Now, continuous pitch control. Now we know that we need to make sure that the what do you say, blade is always in the direction of relative wind, that we have seen, right? So in order to make sure that the blade is always in the direction of wind, we need to have a continuous pitch control. That means at every point, every single point, the power output should be measured and the error should be taken, and then the pitch should be changed accordingly. But in order to do this, this is a very expensive point. This is a very expensive part. So what we are going to do is, if the optimal if the operation cost and the output cost which we are getting do not allow this continuous pitch control, we are not going to establish this continuous pitch control. Okay, and for the smaller machines we don't get this balance, the output power and the pitch control and the establishment cost, those are not balanced for small machines. So we are not going to establish continuous pitch control in the smaller machines. But whatever the machine is, whatever the situation is, we need to install the stalling mechanism. We need to install the stalling mechanism in order to protect the turbine in turbulent weather conditions. In order to protect the turbine in turbulent weather conditions. Whether you establish a continuous pitch control or not depends upon the budget and depends upon the power output and all those things. But if you, whatever the case is, we are going to establish a stalling mechanism. Whatever the case is, we are going to establish a stalling mechanism which will stop the generation at a high speed, higher wind speeds, and protect the turbine from turbulent weather conditions. So this is the pitch control, pitch angle control, ma. So we'll stop here for today's class. We are going to see this stall control, power electronic control, and yaw control in the next class. Along with them, we are going to see what is the control strategy that is being used, and all those things we are going to see in the next class.